Hey, my name's Jonalyn.
I'm Vanessa.
And I'm Kate.
And I'm Matthew San Pedro, and this is Team Huskers 2. Today we will be doing the rotational motion experiment.
Okay, so for this experiment, we'll be demonstrating circular motion and centripetal force.
How are we going to measure that?
Well, we're going to use this system, this apparatus in front of us, and we're going to start by calibrating the system by making sure that these strings are going to be in line with the white line. And we're going to do it by putting it in equilibrium. And we're going to have this
Reference
disc in line with the reference bracket.
Okay. Now, after calibrating, we take the hanging mass and clamp and pulley right here. We take it off, and what happens is the hanging mass is off of equilibrium. Also, before we do that, we would like to measure the radius between the two white lines, and right now it looks like it is 15 centimeters. So after measuring that, we take all of these things off here. And as you can see, it's not in equilibrium.
And let me get a nice picture on the white line. Yeah, far from equilibrium. Okay.
Now to get this from back to equilibrium, we have to use centripetal force and rotational motion by spinning the apparatus until the reference disc is in line with the reference bracket. And once we get that done, we rotate it at a constant speed, and we measure the time of 10 rotations.
Okay, I'll be the timer.
And who wants to spin the apparatus?
I guess I'll be spinning it.
Okay.
All right, let's go.
So we're going to time it 10 seconds, right? Oh yeah, did we explain how the
10
white...
rotations.
Start time.
Yeah.
Stop.
Did it not work?
No, timer didn't work.
Aw.
Well, do we do it?
Hold on, if you can erase it a little bit and be like 8.81 seconds.
Sounds good.
Yeah.
Alright.
All right, we'll do it one more time. We'll wait
good to go.
for the white disc to be at the reference point. And
Okay.
now it's in equilibrium.
White disc is in reference point, right?
Good to go.
Yes.
I think you're a little bit low.
Ah,
Yeah. There you go, that's good.
such a difficult process too.
Yeah. Getting a nice zoom up on it right now. Okay.
8.81 seconds.
Okay.
Okay, sounds good. Now after we get, let's see, that was
Let's
already
go repeat it 3 times, so
3 more
just
times.
to be sure, yeah.
Let's do it with the same one to get an
to
average.
get an average.
Yeah.
Sounds good. Wait till I get it there. All right,
Go.
we're good.
And we're timing this every 10 rotations, right?
Yes.
Okay.
8.97.
8.97? All right. Go ahead and start timing it when you're ready.
This will be our last run.
Ready? Go. .91.
Okay. Now let's go ahead and increase our radius to 15.5 centimeters. So just increase it 0.5 more.
Okay, and dun, 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 now we've changed it to 15.5 centimeters. So we can start doing our second. Okay, just gonna take all this stuff back off again. And we did it right because we
Party
dropped
foul.
stuff. And, okay, are you ready to time it? All right.
Alright, so 10 rotations.
Again.
Okay. Be sure you get that,
Yeah.
a little bit higher.
Higher?
Yeah.
How's that?
That's pretty good.
Okay,
All right.
so that was 9.04 seconds.
Okay.
I'm going to start it again. Okay, that was 9.16 seconds.
Okay. Do it again?
Yeah, one more time. Okay, 9 seconds.
Alright. This is going to be our final trial, and it should be at 16. Ben is going to measure that.
That's 16 right there?
Mm-hmm.
Okay.
Right there.
Alright.
There you go. Okay. I'm going to start timing.
Okay. And John will be our timer for this run. Okay. Oops.
Sorry.
Might have to redo it again.
Gonna do it again.
Yeah.
Okay.
It's hard to do that.
Try to keep
Yeah.
it nice and steady on that equilibrium point.
Yeah.
A little higher. There you go. That's cool.
Okay,
Okay.
run 1 is 9.32.
Okay.
Keep going. That one's 9.29. One more time. .20.
Alright.
One.
Before we start our experiments, we forgot to mention one important point. Here's our apparatus set up at equilibrium, correct? When we take out the hanging mass and it's clamped here, we offset the equilibrium. The hanging mass we use is 150 grams. So in order to put the equilibrium back into balance like this, the centripetal force has to exert the same 150 gram force.
Right.
0.15 times 9.8. That's going to be about 1.47 newtons.
Yep.
So in order to balance that, 1.47 newtons of centripetal force has to be exerted in order for this to set equilibrium. That is why when we begin spinning, we get this to that equilibrium point right there.
Okay, so this is our table. For trial 1, we have a radius of 0.15 meters, and the first run came out to be 8.81 seconds, run 2, 8.97 seconds, run 3, 8.91 seconds, and trial 2, the radius was 0.155 meters, and the run was 9.04 seconds, run 2 was 9.16 seconds, run 3 was 9 seconds. And trial 3, the radius was 0.16 meters. The run for the first run was 9.32, run 2 was 9.29, and run 3 was 9.20 seconds.
After getting all this data, all we really need is the average of each of these times to find out the centripetal force. So to find the average, we had to add the 3 run times together and then divide by 3, which for trial 1 gave us 8.9 seconds, trial 2 9.07 seconds, and for trial 3 the average is 9.27 seconds. And Matt's going to explain to you how we found the centripetal force.
We calculated for the centripetal force. We all know the basic equation, force equals ma, right? Newton's second law. Force equals ma. We also know that the centripetal acceleration in a circle is equal to the velocity squared divided by the radius of the circle. Therefore, by substituting the centripetal acceleration into the Newton's second law, we can come to this expression: force equals mass times the velocity squared divided by radius. We also know that the velocity is equal to 2 pi r, so that it is equal to the circumference of the circle times the number of rotations, in which we timed it to be 10, correct? Divided by the total time it takes for the 10 rotations. Okay, and then we substituted the equation we found for the velocity into the centripetal force acceleration equation, and we were able to come up with this expression. We have the variables, so we solved for our first trial. Our first trial, we used 0.150 kilogram mass. We rotated it about 10 times. We used a radius of 0.150 meters, and we used 8.9 seconds for 10 rotations. And that calculated should be approximately 1.12 newtons. Okay, and we use these calculations for all three trials. Using this average time for all three, we came up with 1.12 newtons for trial 1, trial 2, and 1.10 newtons for trial 3. So it's pretty, our experiment is pretty consistent because of the closest in our answers. Okay.
So why are we doing all of this?
Well, actually, that's a pretty good question. You can take into consideration some real-world things, like that's how a satellite stays in orbit around the Earth without crashing down on us or spinning off into space. It's centripetal force.
Or maybe when we're in a roller coaster and we're going in the loop-de-loop roller coasters, it keeps us.
Right. If there was no centripetal force, we would fall off right on the top.
Right.
Right.
Yeah.
Yep.
Yeah. That would be
Exactly.
bad.
Okay. So what did we just find? We just found centripetal force. This is Team Huskers 2 signing off.